Okay, let's talk about energy. So, if you're here for the first time, just watch the video through. If you're here reviewing, try to answer the questions. Pause the video at a question and try to answer the questions. So, the topic is very broad. So let's see it from several different angles. So first of all, a system, if you want to give it energy, there are two primary ways of doing that. You can do work, or you can use heat. And that distinction allows us to divide energy into two major not categories, I don't want to use that word, two major types. You'll see later that I use the word categories for something else. So two major types. The work side we'll call mechanical energy. I'm not going to write it out. And the thermal side, and the heat side we'll call thermal. And we'll talk about both of those now. But the thermal side is really studied in thermodynamics. And it's the mechanical side that we're going to study now. So let's think of a few examples. Think of an example when work gives something energy. Try to think of a few examples. Pause the video. So the example I'll use is to throw a baseball. You pick up a baseball and you throw it. How much energy it has, let's talk about this mechanical energy. How much energy it has is depends on how much work you do on it, and the work you do on it will depend on the force that you apply, the distance, that's a displacement vector, the distance over which you apply the force, and we'll explain this later on, but the cosine of the angle between those two vectors. So work depends on having a force, applying the force over a distance, and maximizing the work is when the force and the distance, where the force vector and the displacement vector are in the same direction, so the cosine of 0 is 1. And we'll see later if the force and the displacement are perpendicular to each other, there's no work done. We'll discuss that more later. So back to the baseball example. How much energy the ball gets will be a function of how much force you put on it and over how long a distance you throw it. So if you just throw it over a short distance, it's not going to be going as fast with as much energy as if you stretch your arm way back and throw it all the way forward. Okay, so now we have a very precise definition of work. Now when you do that work to the baseball, you give it energy in what form? Well, that form that the energy is in is what we call kinetic energy. So that's what we call kinetic energy, and we can write it as K, or sometimes we'll write it as KE. And pause the video and write down what KE depends on. If you're first time, you'll see the equation 1/2 mv squared. So the mass depends on the mass and the velocity squared. Makes sense. More mass, more energy. More velocity, more energy. How about the square? We'll talk about that more. So the baseball, the faster it's going, and the baseball has a weight, but if we throw a cannonball at the same speed, obviously it has more kinetic energy. All right, now come up with an example of thermal energy, an everyday example. So pause the video, see if you can think of one. Okay, here's my example. My example is going to be cooking. So we're going to cook some soup. So we put a pot of water on the stove, and the stove gets hot from electric energy. We won't trace that back, but the stove gets hotter from burning gas, and the water gets hot, and the food gets cooked. So if we think about our bodies. We can think of examples of work. So we eat food, that's our source of energy, and it allows us to do things like throw the baseball, do work, or it keeps our bodies warm so that they function optimally. So that's an example of thermal energy or heat. Now, when we measure these energies, we measure them in different ways. So let's come back to the mechanical energy. Notice that when we do work, that's newtons. So I'm going to put the units in. Newtons times meters. And that's I'm going to spill over here now. And a newton is a kilogram meter per second squared, and when we multiply that by meters, we get kilogram meter squared per second squared. So that's the unit of energy in its fundamental units. We can also write it as Newton meter, or we give it another name. We'll call it uppercase J for joule, named after a scientist of the name of Joule. So here are three different units for work or energy. A Newton meter, kilogram meters per second, meters squared per second squared, or a joule. Okay, now how about thermal energy? Well, here we go. So how are we going to measure thermal energy? Well, thermal energy is measured by measuring heat. So the unit of thermal energy is the calorie. In the metric system, or the BTU in the British system. And the calorie is defined as, I'm going to have to overwrite this arrow, 1 gram of water raised 1 degree Celsius. Whereas the BTU is defined as 1 pound of water raised 1 degree Fahrenheit. So you see how we measure that. It's just a measure of how much energy we transfer to things by measuring their temperature, which is an indication of how much heat something contains. Okay, I very nicely tucked that away where you can still see it. Now I want to just switch for a minute. Well, let me just review briefly. We divided energy into two what I called energy types. And the types are according to mechanical and thermal. Mechanical energy is added or subtracted from things by doing work. And thermal energy is added or subtracted systems by putting heat in, by putting them in contact with hotter objects. Okay, now I'm going to take a different tact, and we're going to talk about the categories of energy. So there's really a wide diversity of energy types. If we start naming all the energy forms we can think of, the conversation could go on and on. So there are these three categories that are useful because all energy types that we think of, no matter what it is, of the many, many different types, can be fit into three categories. And so the first is kinetic, which we already mentioned, the energy of motion, and up above we have the equation for that. And so any object that has mass is going to have kinetic energy according to the equation written up above. The second category is a very broad category called potential energy. and it's energy in a stored form. And there are many, many, many types of potential energy. We'll list those in a minute, but I want to first mention the last or third category, and that's radiation. And radiation, in its full term, is electromagnetic radiation, and it includes some obvious things like light, but also infrared radiation, ultraviolet radiation, microwave radiation, and X-ray radiation, gamma ray radiation, which is nuclear radiation, etc. Those are all different forms of radiation. So kinetic is simple, energy of motion, 1/2 mv squared. Let's talk about potential energy. So for us, we're going to deal with two very narrow slices of potential energy, and those are the ones you need to know about. And one is, so we're going to use, there's two ways if we write potential energy. PE is often used, and so the first type of potential energy is gravitational potential energy. So we write that as PEG, or on your equation sheet you'll see UG, because in thermodynamics U is the term that's used for energy. So we'll be able to use each of those terms. And gravitational potential energy, no surprise, how much something has because of its position depends on the mass of the object times g, that's the weight of the object, times the height. So sometimes we write it as mgh, or mg delta y. So if I have a 1 kilogram mass and I raise it from the floor to the table and say it's 1 meter, then I can calculate the energy stored in that mass as gravitational potential energy. And a good everyday example of gravitational potential energy is water flowing over a waterfall. That water flowing over the waterfall has gravitational potential energy and can be used to turn turbines and generate electricity. Another example might be a pile driver, where you raise a heavy weight using a crane and then you drop it onto a steel beam and drive it into the ground. The other form of potential energy that we'll talk about in the 2 weeks we study energy is potential energy spring, or U spring. And spring potential energy depends on how stiff the spring is and how much we stretch or compress it. So the equation, which we'll talk about in more detail later, 1/2 k x squared, where x is the amount that we compress or stretch the spring, and k is the spring constant. And just for completion, I know this is a lot of information, I'll write down what the spring constant is. The spring constant, k, is measured by applying a force to the spring and seeing how much it compresses or stretches. So that ratio of force to compression or stretching is the spring constant. It's also called Hooke's law. All right, just in getting the big picture, so these are the forms of energy we care about. In fact, most of the equations we need are here for the work we're going to be doing. We have our definition of work. We have our definition and way of calculating kinetic energy. We have the way of calculating gravitational potential energy and spring potential energy. And we have the equation for finding the spring constant, or relating the force of a spring to the spring constant and its compression or extension. That's called Hooke's law. So there's one more equation that I'll talk about later. But in just completing our discussion of potential energy, most of the energy that we deal with in our lives falls into a very broad category of potential energy, and that's called chemical energy. So I'll just write that down. Chem energy. And that includes, I'm not going to have space to write it, but it includes all the things that we burn, such as coal, oil, natural gas, wood, or more generally biomass, if you're familiar with that. And it also includes like chemicals in batteries. So batteries an important way of storing energy in our current technological society, and so batteries use chemical energy to drive electricity through electric circuits, to run our cell phones and our calculators, and start our cars, and sometimes now with electric cars even run the cars. So that completes our overall general, no, actually there's one more thing. So the last and perhaps most important thing is, one of the reasons energy is so important is that it's a quantity, whether it's mechanical energy or thermal energy, whether it's work or heat, whether it's any form of potential energy or radiation. It has this quality that it's never created or destroyed. So the uniting idea in the energy world is what we call the law of conservation of energy. And we often say energy can't be created or destroyed, but a better way of saying the law of conservation of energy, and we don't like writing this out all the time, so we call it LCE, the law of conservation of energy, is, and I'll just abbreviate this, energy, let me pause the video and write it. So there's the best statement of the law of conservation. Energy of a closed system is a constant value. In other words, in a closed system, energy can't be created or destroyed. It has to stay constant. And our equation, which you'll see on the equation sheet for this, is that work done by non-conservative forces, we'll explain that in a minute, is equal to the change in kinetic energy plus the change in potential energy. So that equation is our conservation of energy equation. And the only way to fully understand this is to actually use it, and we will use it. But what it's saying is that if we have a system where no work is done, that means no energy is added or subtracted from the system. And so any change in kinetic energy has to be offset by a change in potential energy. And so in class we'll see many good examples, but the example I like the best is an oscillating mass on a spring. So I attach a spring to a bracket, and we put a mass on the spring, and we lift or drop it, and it oscillates back and forth. And so this, in the short run, it's a closed system. I mean, it is going to lose energy to air resistance and heating the spring and some other forms of outside work, but for the most part, this thing will oscillate back and forth for a very long time, where at the top it has a lot of gravitational potential, at the bottom it has a lot of spring potential, and in the middle it has kinetic. And so this system is a mixture of kinetic energy, gravitational potential energy, and spring potential energy, all in one system, where the total energy of the system will remain constant over the short run. As I said, it does leak off slowly because there is some work done, by air resistance, and also some work as the spring stretches and compresses. It actually heats up a little bit, so some energy leaks off into heat. So this work by non-conservative forces, another example would be if I had a block and I slid it across a frictionless surface, then I would set it in motion with a little bit of energy, and it would just go at a constant velocity without the energy changing. But in most cases, the block's going to slide and then stop, and that's because there's work done on it due to the force of friction, and that's a negative energy, and that takes energy out of the system. So over the course of the next 2 weeks, we'll look at many, many examples where we're using all these equations. And our workhorse, our unifying equation, is this law of conservation of energy equation. And so this is what you need to practice using. And the MOPS and the Moodle questions will all help you develop a good understanding of this equation and how it relates to all these other equations that we discussed. Okay.